Hey physio fans, welcome. Let's talk today about the sliding filament theory. So first we need to just identify a couple of pieces. Now this right here is called actin. It's also known as the thin filament. And over here we have myosin, also known as the thick filament. Now I know that in this picture they really look about the same in thickness, but you'll see why the myosin is considered thicker in just a minute. Now it's also important to know that before the muscle cell can contract, we have this piece called tropomyosin. Tropomyosin is covering up the actin. That matters because the actin have these little dots on them. Those are called actin binding sites. And basically what we want to happen is the myosin has these little arms that are going to reach up and grab those binding sites. But in order for that to happen, tropomyosin needs to be out of the way. Now tropomyosin is controlled by a little receptor called troponin. Troponin responds to calcium. If you remember from the part 1 of this video, calcium has just been released from the sarcoplasmic reticulum and it's going to come and activate the sliding filament theory. It does that by binding to troponin. Now when calcium binds to troponin, that allows tropomyosin to be moved out of the way so that those actin binding sites are now free. So now we need those myosin heads to reach up and grab onto the actin binding sites. That is called the cross bridge. They reach up, grab those actin binding sites. It's important to note that bound to the myosin is a molecule of ADP and a molecule of inorganic phosphate, or PI. The next step is to make this space right here smaller, to pull the strands of actin closer together. And we're going to do that in what's called the power stroke. So we pull like this. Those little heads are now at an angle. And we still have that ADP and PI bound. That is called the power stroke. I want you to think of doing a bicep curl. Your arm is extended, then you use energy to pull that weight closer to your shoulder. That is the cross bridge and the power stroke. Now we need to do this over and over and over again to facilitate a contraction. We need this space to just get smaller and smaller and smaller. So we need those myosin heads to be able to release. It's interesting that we actually need energy in order to be able to release the myosin heads. You would be tempted to think that it's the power stroke, but it is the release. So what we're going to do is we're going to get rid of our ADP and PI, and we're going to need a molecule of ATP. Now that we have that, our myosin heads are able to release and let go of those actin binding sites so that we can start the contraction over again. The last step is the recovery. So you'll notice that these heads are still bent at this angle, but we need them to be back at this angle so that they can pull one more time. Actually, one more time. They're going to do this thousands of times for every contraction. And what we need for that is we need ATP to become ADP and PI. Once ATP has been phosphorylated, that just means that we're going to kick off one phosphate group. So it goes from ATP to ADP and a loose phosphate group. These myosin heads are able to swing back into that other position, which allows them to pull again. And this process is going to happen over and over and over again. That's what allows a muscle cell to contract. So to recap, the cross bridge is when the myosin heads reach up and grab the actin. The power stroke is when they pull the strands of actin closer together. The release is when they let go, and the recover is when they move back into position so that they can repeat the process. Now, if this video was helpful for you, please give me a like and a subscribe so that I can help other people find these videos that have the same questions as you.